All right, seeing as there were no further questions from yesterday's assignment, let's get right into the final lesson in this unit, which is section 3 of chapter 2. It's called Solving Radical Equations Graphically. And sometimes I feel the need to explain to you the rationale behind what Alberta Education does and what the diploma exam branch of Alberta Education does to make you understand why we're learning what we're learning. First of all, the concept of solving a radical equation being solving an equation like this one is something from Math 20-1. In that monster unit in Math 20-1 called, what is it called? Absolute value functions, radical functions, and reciprocal functions. It's this beast of a unit. It's all over the place. Somewhere in there, among all the other radical arithmetic and algebra you do, you learn how to solve these equations. A radical equation is an equation where the variable that you're trying to solve for is part of a radicand. In other words, it's under the square root. So if you look carefully at the title of this lesson, it says Solving Radical Equations Graphically. And according to the program of studies or the curriculum guides, Math 30-1 students are expected to know how to solve these equations graphically, but not algebraically. However, the diploma exam will sometimes have, and I will have on the unit exam, questions where you need to solve things algebraically anyway, because you're going to be asked to determine on the diploma exam what are called extraneous roots, which I will review with you in a bit. And the only way to determine an extraneous root is to do the work algebraically. When you solve any equation graphically, if there's an extraneous root, you will never see the extraneous root. So although your textbook only talks about graphical solutions, I need to talk about algebraic solutions. So we're going to review the algebraic methods of solving radical equations that you learned about last year or last course in Math 20-1, and that includes finding extraneous roots, which I expect you to, in my Math 20-1 class, I expect you to find those roots. By the way, the word root is just a synonym for solution. So when I say what are the roots of an equation, I'm asking you for the solutions to the equation. We're going to find approximate solutions to radical equations using graphical methods, which ties us into the connection between X-intercepts and solutions to equations. And there are other ways that we can solve things graphically. The last two bullets here are things that shouldn't be new to you. Don't try to decipher what I mean by that. I'm just going to come back to that idea later and say, you can do this with any equation and it should have been taught to you already. So the first thing is, number 1 says state the restriction on x in that equation. And sometimes on a diploma exam and an exam, and it's a valuable skill to have, you need to know what the restriction is on the variable. The bottom line here is that when you have a radical expression, the thing under the radical is called the radicand. Have I taught you the word argument? I have. So the argument of a square root function is called the radicand specifically. And your restriction will always be that the radicand must be greater than or equal to 0. Just like you couldn't take the square root of a negative y in the last lesson, you can't take the square root of a negative radicand. So what does that translate to in this particular question? Well, if this is the case, and you look at that equation, then it means in this case x plus 10 must be greater than or equal to 0. And that's a very simple inequality for us to solve. It's a linear inequality. You just rearrange it for x, and we end up with the statement that x must be greater than or equal to negative 10. I find it is helpful to communicate that on a number line. Again, I've mentioned this before, I'm a big fan of number lines. They're very informative in terms of numbers and domains and things like that. What I'm saying is that x can be equal to this number, or x can be any number to the right of that number. So that's a way of stating the restrictions. You know, can we call this the domain of x's? I guess we could, but this has nothing directly to do with a graph, because when you take a look at the equation, well, there's no y. It's just an equation. Any questions with the restriction on x there? A restriction is just a confinement. It's saying this is what x has to be. Otherwise, it won't work. All right. So solve this equation algebraically. There's kind of a two-step, maybe you could call it a three-step process, but I think two-step does it. A two-step process in solving radical equations. The first step is you isolate the radical and square both sides. In other words, the first step is get rid of the radical. And in this particular case, all I'm going to do is rewrite this equation as root x plus 10 equals 4, and then square both sides. So this is my first step. Eliminate the radical. How do you do that? Get it by itself and square both sides. When we square a square root, of course, those two operations undo each other because they're inverse operations. And when I square 4, I get 16. This is turned into a childlike question. X plus 10 equals 16. So if you want to solve it formally, you subtract 10 from both sides. If you want to just look at it and say, well, 6 plus 10 gives you 16, that will do the trick as well. So x is equal to 6. Now, in Math 20-1, you're taught that funny things happen when you square both sides of an equation. And sometimes what one of those funny things is that you end up getting an answer that if you put back into the original equation, it doesn't work. And if that is the case, then the answer that you've got is not really a solution, but we call it an extraneous solution or an extraneous root. Because of that, you always want to check your solution that you get in the original equation. I can't emphasize that enough. Don't put it in anywhere else. You have to put it in the original equation. So this will be something that we deal with a lot in trigonometry when you're checking the validity of something. What you want to do is leave the equal sign out. You don't want to have an equal sign there because we don't know if they're equal yet, although it's pretty obvious they are. Okay? And you write the left-hand side of the original equation, which is root x plus 10, then minus 4. You write the right-hand side, which is 0, and then you substitute in the value of x that you found. Well, we found x equals 6, so this is going to become that. 6 plus 10 is 16. And I've written an error here, haven't I? Should be minus 4. Let me repair that. This is minus 4 in the original equation. So then I get root 16 minus 4. I mean, it's, like I said, this is a very simple equation. You could probably see right away that it works because root 16 is 4. So we have 4 minus 4, which is 0. And on the right-hand side, we have 0. So what we write mathematically is left side equals right side for this particular value of x. It's how we conclude our exploration here. And what this means is that this is a solution. I want to be careful here. If you were writing a written response, don't just put a check there. Put it is a valid solution. Like write it out in words. Okay, find the x-intercepts of the graph of this function. I hope it's not lost on everybody that the equation we're trying to solve is root x plus 10 minus 4 equals 0, and the equation of the function we're graphing is f of x equals root x plus 10 minus 4. And we're asked to find the x-intercepts. Well, first of all, before we do that on the graphing calculator, if I said to you, find x-intercepts of a function, x-intercepts are where y equals 0. That's what you're taught. How do you find an x-intercept? Change y to 0 and solve the equation. So I hope you understand that if we take this function here and change y to 0, it will turn into this equation here, which means the x-intercepts have to be the solution that we found, right? This is the broader picture when I said this third bullet is something you should already understand. This third bullet is simply saying if you zero any equation in the universe and find the x-intercepts graphically, you will be finding the solutions to that equation. I'll talk a little bit more about that in a bit. So on our graphing calculator, just a little bit of procedure here. How do we find x-intercepts on the graphing calculator? Well, you plot the graph by entering the function in for y1 in this case, the square root of x plus 10, close brackets on the square root argument. Otherwise, you're going to continue to square root everything after that, then minus 4. My go-to zoom setting is probably almost always zoom standard. That will change when we get to trigonometry. I can see what appears to be an x-intercept someplace in this region here. To find an x-intercept on your graphing calculator, now you go to your calculate menu. Choose, it's interesting that the title of the option that finds x-intercepts is called 0. And it's called 0 because it's where the function equals 0. That's the meaning of the word 0. So I choose 0, and then it says left bound or left boundary. So I have to put my cursor someplace to the left of that x-intercept where I see it visually. There's only one x-intercept, so I don't have to worry about precisely how close I am. If there were more than one, then you probably want to hedge your bets and go a little bit closer to the one you're interested in. Hit enter. And then scroll. You can hold the key on your calculator. I can't on this emulator. It will think I want to right click. Make sure you go past the x-intercept to the right, hit enter. Guess, you don't need to guess. Don't worry about why it's even there. And it tells you that the 0 of that function, which means the x-intercept of that function is 6. So the x-intercept equals 6. What do you notice? The x-intercept of the function is the solution or the root to the equation. And that's a pretty powerful idea. It should have really been taught to you a little bit in grade 10. You certainly talk about it in grade 11. What this means is without having any understanding of math, I could teach a grade 3 student how to solve an equation. If I said to a grade 3 student, solve this equation. Of course, there's a more formal way that we would do it. We would add 1 to both sides to get 2x equals 8. Divide both sides by 2, you get x equals 4. And we understand what we're doing. We've learned along the way why these steps work. And they work because they're the opposite operations to what's happening to x. But I could teach a grade 3 student, I could give this calculator to them, and I could say, well, here's what you want to do. You want to go in here, well, maybe a grade 3 student, this would be a little difficult. I'm going to subtract 7 from both sides. This first step, maybe not a grade 3 student, but I could definitely teach the grade 3 student how to solve 2x minus 8 equals 0. You understand the solution's 4, right? I mean, you don't even have to, you just look at it, it's 4. But I could say, just go ahead and enter this. And then they go, okay, what do I do now? And I could talk them through it. I go zoom 6. They may not understand what this picture even means. It doesn't matter. They haven't been taught about coordinate planes. And then I go find out, go to your calculate menu and choose 0. Why? Well, because that's the next step. find that point where that slanted line crosses the horizontal line and scroll until your little flashy thing is to the left of it, hit enter, scroll until your little flashy thing is to the right of it and hit enter, and they get 4, right? Of course, I wouldn't be doing them any justice because they wouldn't be learning any math. So this part right here is the most significant idea. Is the most significant idea so far. It's got nothing to do with radical equations so much as it has to do with that concept. Which means when we get into trigonometry, and some of you struggle with trigonometry, which you will, if I give you the following equation with a little bit of explanation in the unit as to what sine squared of x means. Although it's an expectation you can solve it algebraically, you can certainly solve this graphically. It's a little more complicated because you have to worry about degrees versus radians and other things. So don't worry about the solutions to this. All right, let's take a look now at example 2. What's the restriction on x in this example? Well, this is very simple. We go x plus 5 is greater than or equal to 0, which means x is greater than or equal to negative 5. Because the radicand cannot be negative, it must be greater than or equal to 0. So we could symbolize this on a number line, a one-dimensional graph. By saying that that shows the allowable values of x. No problem there, I don't think. Solve this equation algebraically. So we've already isolated the radical, right? The radical is already by itself. So I'm just going to rewrite this. Root x plus 5 equals x plus 3. And I'm going to square both sides. We don't really need the brackets around the left side, but I like to put it there. And when I square the square root on the left-hand side, I get x plus 5. And now comes something that is, for math teachers, this can be very frustrating. At this point in time, everybody should know what x plus 3 quantity squared will give you. It's going to give you x squared plus 6x plus 9. And I will explain why in a second, but this is something that really irks math teachers. Not me so much, as I just explain it every time, but some math teachers get really upset. Because what you should have learned in grade 9 and 10 is that x plus 3 quantity squared means x plus 3 times x plus 3. And that means you have to apply the distributive property. In other words, you have to FOIL that out. Right? You guys have all been taught the word FOIL, first, outer, inner, last. So first is x squared, outer is 3x, inner is 3x, and then last is 3 times 3, which is 9. And there are some teachers who just say, you know what, I'm not going to explain this to you every time. You should know that. And what I have learned over the years is even in my calculus class, I get students sometimes writing x squared plus 9, which is like, you know, the vein in my forehead starts bulging. It's a very, oh man, why are you doing that? So rather than getting annoyed by it every time, you will find me just saying off on the side a reminder that that's what it means. I will not in the future write all of this, but what I almost always write is just remember it's x plus 3 times x plus 3. So now this is a Math 20 equation. Because it has a quadratic term, it has an x squared, I need to zero the equation. What does that mean? It means move all of the terms to one side. So I'm subtracting x from both sides, and I'm subtracting 5 from both sides. And I believe that's right, but, you know, 42 i's are better than 2. Does that look okay? Okay. Then you're in the realm of quadratic equations from Math 20-1, and you say, well, how do I want to solve this? Well, I could solve it graphically. You were taught how to solve these equations graphically last year. But the question says solve it algebraically, so that's out. I could solve it using completing the square. I don't think anybody in the room wants to complete the square of this to solve this equation, because I don't think too many people would even remember what that involves. We could solve it using the quadratic formula. That's always a surefire success, but I think factoring is the quickest option. In this particular case, two numbers that multiply to give 4 and add to give 5 are 1 and 4. So this factors into x plus 4, x plus 1. What does that mean? Well, it means that x plus 4 can equal 0, or x plus 1 can equal 0. Let me explain this. It's not that I feel the need I have to teach you prior math, but I think this is an important idea, particularly for Unit 2. Which is polynomial equations and functions. The reason this works is that if you have things that are factors are things that are in their own set of brackets multiplied by other things in brackets. If you have factors that are being multiplied, if one of those factors happens to be equal to 0, the whole thing will equal 0. If x plus 4 is 0, I don't care what x plus 1 is. 0 times x plus 1 will give you 0, and that's what we're after. So you set each factor equal to 0 when you solve this equation, and you get x equals negative 4 and x equals negative 1. Now, I want to point something out to you, because there's a problem with the Math 20 textbook, and I've seen some teachers actually repeat this problem. If I go back to the first example, this is a little tricky. Look at the restrictions. Look at the restrictions on x. X has to be greater than or equal to negative 10, right? In that equation. And when we solved this equation, we got 6. Are you with me? Is 6 a number in the allowable values of x? Yes. The mistake is that your Math 20-1 textbook, I'm baffled by this, says that as long as the number you get is in the allowable values, it is a legitimate solution. And that is flat out wrong. And you may have even been taught that last year. It is not correct. Just because the number you get falls in the acceptable values of x doesn't mean it's a solution. If we take a look at these two solutions, what did we get? Negative 1 and negative 4, right? Where is negative 1 and negative 4? Negative 4 is here. Negative 1 is here. These are both numbers that are in this domain, right? But let's check them now against the original equation, which is what we have to do. We have to check for extraneous roots. The original equation had, on the left side, had root, I can't even remember now. Let me look. X plus 5. And the right side had x plus 3. Am I right there? Am I correct in writing that? Okay. So if I check now with one of our solutions of negative 4. On the left-hand side, I get root 1, which is 1. And on the right-hand side, I have negative 1. Well, 1 and negative 1 are two different numbers. And don't say, well, yeah, but what about the plus or minus on the left? There is no plus or minus. There's a plus or minus if you introduce a square root, and we didn't. So this tells us the left side is not equal to the right side for negative 4, and that tells us this is not a solution. It's extraneous. And I've always hated the phrase extraneous solution because it's saying it's a type of solution. And it's not a solution. Okay, extraneous solution means it's not a solution. If we do the same thing with negative 1, I'm not going to rewrite the equation. We will have the square root of negative 1 plus 5. We will have negative 1 plus 3. I end up with root 4 on the left. I end up with 2 on the right. So 2 equals 2. And I can say in this case, the left side is equal to the right side. So I can verify that that's a solution. My brain just locked up. What time does this class end? 10:35 approximately? Oh, we got lots of time. Okay. Any questions with the algebraic solution to that equation? Okay, now could we solve this graphically? Well, I'm going to solve it two ways. I'm going to solve it the way the textbook wants you to solve it and the way the curriculum guide wants you to solve it, which is to use intercepts or use X-Intercepts. That involves taking the equation and zeroing the equation so that you can equate 0 with y Let me rewrite that. That's pretty sloppy. So we can equate 0 with y and get y equals the square root of x plus 5, then minus x minus 3, and find the x-intercepts of that function. Which is bullet 3 in the objectives. Okay, so the square root of x plus 5, and then we have minus x minus 3. Zoom 6 won't always be the best option, but I think it's a good start. Well, no, it is the best option if you don't have any other choices. That's your starting point. It's a real weird graph. It starts in the middle of nowhere. Just so you know, it's not crucial to answering this question, but there's a little bit of a bump to this graph. It goes up a little bit and then down. Really not that important. But when you look at it, there is only one x-intercept, isn't there? So if we find that x-intercept, which is the solution to the equation, we go to our calculate menu and choose option 2, which is called the 0 of the function. Move our cursor to the left. Hit enter, move it to the right. Hit enter a third time, and we get -1. So when we solve this graphically, we get the solution x equals -1. And that's the only x-intercept, which means it's the only graph. I like method 2. It's a matter of preference. Method 2 is going to take this equation, root x plus 5 equals x plus 3, and we're going to graph two functions. We're going to graph y1 and y2. And wherever they are equal is a solution for x. And what does that mean, wherever they are equal? Wherever they cross. My main reason for doing this is I don't like having to scroll to the left and the right, because some functions have an x-intercept that occurs where the graph is very steep, and it's hard to put the cursor to the left and the right. Whereas this, let me show you what you do on your calculator. Your first function is the square root of x plus 5. Your second function is x plus 3. We graph it. Here's the square root of x plus 5. Here's x plus 3. I want to find the intersection point. When I go to my calculate menu, I'm going to choose option 5, which is intersect. The nice thing is, and there might be the odd exception to this, but if all you have are two functions and you can see the point of intersection, you don't have to scroll at all. You just go enter, enter, enter. Now, if there's more than one intersection point, then you might have to scroll close to the one you want. But it just says first curve. Okay, second curve. It hops me to the other curve. Guess? I don't think so. And you get -1. So regardless, x equals -1 is the solution. Notice, by the way, that when you solve graphically using method 2, what I'm calling method 2, we don't care about y. It's all about x. And the culmination of this is, what do you notice about the extraneous root that we found when we did this algebraically? Remember that we had, I believe, you'll let me know, we had this solution which was not correct. Am I right? Okay. And we had this solution which was correct. What do you notice about the extraneous root when we went to solve it graphically? We don't see it. This is not visible graphically. And it's not visible graphically for a very simple reason. It's not a solution, so why should they cross at that point? If they crossed at that point, it wouldn't be extraneous. And this goes full circle back to where I started. In this course, you were asked for the value of the extraneous root, so you need to know how to solve it algebraically. So think about that. If I said, what is the value of the extraneous root for this equation? You have to solve it algebraically to find the value of x that doesn't work. Okay. Couple more questions. Solve this equation algebraically. So we're going to square both sides. We have 3x squared plus 4, nope, minus 5 under the radical. We're going to have to square that in a bit. We have x plus 4 here. So we're going to square both sides. Now, you'll notice I didn't say determine the restrictions. Because, as a side note, and you don't need to write this down, determining where 3x squared minus 5 is greater than or equal to 0 is a very tricky bit of business. It's something you were taught in 20-1. I don't expect many to have remembered it. But we will look at better ways to find out where this is greater than or equal to 0 later in the course, rather than going back and doing something in 20-1 that's really awkward. Okay, so we're not going to worry about restrictions here. So I square both sides. I get 3x squared minus 5 because the squaring and the square rooting go away. I remember, of course, that x plus 4 quantity squared means x plus 4 multiplied by x plus 4, which gives me x squared plus 4x plus 4x plus 16. I look at it now and go, well, it's quadratic. So I've backed up into Math 20-1 now. What does that mean? It means that I should zero this equation, subtract x squared from both sides. I have 8x on the right. I better subtract that 8x from both sides. I have 16 that I need to subtract from negative 5. How is my arithmetic? I mean, I guess it's algebra, but I'm just dealing with numbers. Does it look okay? All right, so now, and I'm sorry, I get confused between all the courses I teach. Have I taught you guys, or have I mentioned in this class the significance of b squared minus 4ac in terms of factoring? I don't think I have. b squared minus 4ac is part of the quadratic formula. If you were to look at the quadratic formula, I was going to bring it up on the formula sheet, but I can probably write it out just as quick. The quadratic formula is this, and that b squared minus 4ac is part of the solution to a quadratic equation. Now, if b squared minus 4ac is a number like 4, then in your solution to the quadratic equation you're solving, you will have plus or minus root 4, which is plus or minus 2. And there's no radicals in that. This is really important. If there's no radicals, that means you didn't need to use the quadratic formula to solve it, and what that means is it's factorable. And what I'm telling you is that if b squared minus 4ac equals a perfect square, then it's factorable. And the reason why I feel that's important is I don't teach you a specific way of solving or of factoring this type of expression. I'm pretty sure I haven't asked you this before. How many of you remember in grade 10 you're taught this method of decomposition to factor this kind of thing? Probably not. You were taught it. You probably didn't learn it, but we teach it. I use trial and error. And if this thing isn't factorable and you're going to use trial and error, you're just going to get frustrated. Because you try this and it doesn't work, you try this and it doesn't work. So I always recommend, if you're unsure, find b squared minus 4ac first. I would like you to calculate b squared minus 4ac. And the negatives are important here, so you would have to calculate negative 8 quantity squared minus 4 times 2 times negative 21. I want to say 232. Don't forget, you need brackets around negatives when you're squaring. 232. 232 is not a perfect square. So I can't waste my time factoring this because it's not factorable. This is Math 30-1. Math 20-1 has a huge component in it about quadratics and solving quadratic equations, which is why when you look at your formula sheet, you'll see the quadratic formula. The nice thing now about solving this with the quadratic formula is we've already calculated b squared minus 4ac. So this becomes x equals negative b. If b is negative 8, then negative b is 8, plus or minus root 232, all over 2a, which is 4. Are you with me? Okay. There's something else from previous courses that we need to talk about here, and it's the fact that you can simplify root 232. And I'm not going back and dredging up all of these other things because they're unimportant. They're important. So if we take a detour and talk about 232 as a root, we want to express radicals in simplest form. And that means your job right now for me is to find two numbers that multiply to give 232, and one of those numbers needs to be a perfect square. And I'm going to push the envelope here and say I want the biggest perfect square. Then we'll talk about what happens if you don't find the biggest perfect square. So you got to play around on your calculator and find a number that divides into 232 that's a perfect square. Like 4 or 9 or 16 or 25 or 36, 49. And when you've found one, ask yourself if there's a bigger one. I want the biggest perfect square. And I realize now after saying that there's no trick here. I think 4 is the biggest perfect square. I don't think you get a number bigger than 4. Because this number, here's why I know there's not a bigger perfect square. If there was a bigger perfect, and it's 58, 4 times 58. If there was a bigger perfect square bigger than 4, then there would also be another perfect square in 58. And there isn't. 58 is, I believe, 2 times 29, which are both prime numbers. And what that means is that root 232 is 2 root 58. This is something you're going to have to do a lot of in trigonometry in this course and in other units. So root 232 is 2 root 58. Going back to our question, that means that x equals 8 plus or minus 4, nope, plus or minus 2 root, I don't know whether it's because I just get on autopilot and don't think. I don't slow down enough, but I slip a gear from time to time in my head. Is that better? Okay. Am I allowed to do what I just did in green? No. What could I do instead? Reagan, do you know? So if I understand what you're saying, I have to cancel a 2 from the 8, from the 2 root 58, and from the 4. I have to reduce by the same factor all 3 of these. Okay. And that's kind of the shortcut I taught you when we first learned this in Math 20-1, which means we get 4 plus or minus 1 root 58 all over 2. So going a little further, can I cancel the 4 and the 2? No, because the number in here is a 1, and I can't reduce that anymore. But then, and it's a good thing we have lots of time. This is a rather short lesson, but there's so much math embedded in it that's really crucial. There are people in this class that I suspect they're in grade 11, and I suspect next year they'll take calculus. And this is important for calculus as well as the rest of this course. The reason that works is, and you've heard me say this if you've had me as a teacher before, you can only ever cancel something if it's a factor in the numerator and denominator. That's what canceling is all about, canceling factors. So when I look at the numerator here, I can factor out a 2 and be left with 4 plus or minus root 58. And when I look at the denominator, I'm not sure why you would want to do this, but I can factor 4 into 2 times 2, can't I? And the key thing is factors, and I already mentioned this once today, factors are things that are in their own set of brackets multiplied by everything else. That's visually how you identify a factor. So there's a factor of 2 in the numerator. There's a factor of 2 in the denominator. That's what you're really canceling. This bit of business here and kind of going from here right to there was just a shortcut I taught you before we talked about factors. So anyway, when you cancel that, that's what you get. Now, we're not going to check those by putting them into the equation. Let's solve this graphically. Here's a nice way you can check to see if there are any extraneous roots. Let's solve this graphically. I'm going to go with the y1, y2 method if you don't mind. Well, that's not a question. I'm going to go with the y1, y2 method. So the first one is the square root of 3x squared minus 5. The second one is x plus 4. By the way, you should recognize this graph. This is what we learned yesterday. The calculator does kind of a crappy job in graphing this because the original function 3x squared minus 5 will look like this. So this is the square root function. This is what we learned yesterday. So the crappy part about your calculator, is that it doesn't quite connect them with the x-axis, but it's there. You can see there's two intersection points, can't you? Then there's 2 solutions. And if there's 2 solutions, there are no extraneous solutions because we only got 2. Any questions with this example? Ian?
So on the calculator, the square root function, it does reach the x.
Yep. Okay. Yep. You know, this is the big time. This is Math 30-1, so as a numerical response question, this is perfectly valid at this level, that the solutions are x equals a plus or minus root b all over c in simplified form. What are the values of a, b, and c? Well, a is 4, b is 58, so you would use 2 of the boxes in the numerical response for that, and c is 2. I don't really like that as a question because it's more a Math 20 question, but there you go. We have one last example here. Oh, well, I guess we've solved this graphically. We can take a minute and find the values. Did anybody find them already? A couple people. So if I want to find the values, this is kind of what I was talking about earlier when I said, you know, when you use this method, you can kind of close your eyes and hit enter 3 times. That's not exactly true in this case. You need to go close to one of the x-intercepts. In fact, when I first did that, it dumped my cursor in between there, and one of the functions didn't even exist. So I hit enter 3 times. I get negative 1.81. I repeat the process, but I scroll over to the right. By the way, you don't have to scroll over to the right. You could just say that I'm going to use x equals 7 or 5 and put in the x coordinate. I guess you can't. I thought you could. My mistake. I guess you have to scroll. I don't know the exact way your calculator does it, but my thinking is just get closer to that x-intercept than the other one. And then hit enter 3 times. By the way, we had x equals, was it 4 plus or minus root 58? I'd be willing to bet a large sum of money that if you take 4 minus the square root of 58, oh, it's over 2? Okay, if you take 4 minus the square root of 58 all over 2, you're going to get negative 1.807. And if you take 4 plus the square root of 58, then hit equals and then go divided by 2, you're going to get 5.807. Okay. One last question. It's a word problem. So let's take a minute and dissect this. The speed of a roller coaster car that has an initial speed of v sub 0, if it falls a distance d, is given by that formula. So v equals the square root of VO, which is the initial speed squared, plus 2AD. What are we told here? The acceleration due to gravity is A, and it's 32. The speed at the bottom is 130 feet per second, and the initial speed is 8. By the way, just as a note, for those of you taking, is anybody in Physics 20 right now by chance? Physics 20? Have you done the kinematics formulas yet?
We're in the midst of
Okay. And many of you have taken Physics 20 and possibly Physics 30. This is just a variation of VF squared equals VI squared plus 2AD. It's just solved for VF. And some of the notation's a little different. The other thing, of course, is they're in imperial units, but that doesn't change the fact that it's the same equation. So we're told V at the bottom is 130. The acceleration is 32. And what else are we told? The initial speed, which is v0, is 8. You're asked to find the distance. So this is a radical equation. You're going to put in those numbers. 130 equals the square root of 8 squared plus 2 times 32 times d. And I'm really not sure the likelihood of you getting a question like this on an exam, but I'm giving it, you could, but I'm giving it to you to demonstrate to you that it's a lot quicker to solve this algebraically. And the reason is, if you solve this graphically, you're going to have to play around with where the graphs intersect, which is a confusing thing. How many of you remember that trying to find an intersection point was a point of frustration last year sometimes? You had to get the right window settings, and then you just start sweating and go, geez, did I enter it wrong? You second guess yourself. Look, this is simple. Square both sides. I think 130 squared is 16900, but you can double check that. When I square the right side, the square root goes away, and I'm left with 64. 8 squared is 64, plus 2 times 32 is also 64d. You can solve this. It's why I don't believe this is really a Math 30 level question. It's just too simple. But I'm demonstrating to you that if you go to solve a radical function graphically, and you can't see the point of intersection, maybe you should solve it algebraically instead. It might be more work, but it's surefire. Subtract 64, you get 16836. How's my subtraction? Good. Equals 64D. I'm not going to attempt to divide 64 into that number in my head. That would just embarrass all of us. 16832 divided by 64. Oh, 16836 divided by 64. It's about, wow. Oh, that's feet. I thought that was meters. It's going 263 meters. That's like 2.5 football fields long, but it's feet. 263 feet, approximately. You know, whether you round up or down or how you round it depends on what the question says. Right? To the nearest meter would be 263 feet. To the nearest foot would be 263 feet. Any questions with that final example? Okay, so you have some questions to practice here. That's it for the unit. This ends chapter 2 and ends the unit. You also have those other questions that I mentioned on page 58 of your textbook this morning in the seminar that you can be working on. You got lots of time here. I will get you the review stuff maybe by the end of the class, because some of you like to get a little bit of a jump on that stuff. So I'll be around in a bit to help you out.